NF3. This one's going to obey the octet rule.
Yeah.
Okay, so no problem with that? Okay, what was the next one?
BOH3.
BOH3.
But the side's in parentheses.
Like this. This one will not obey the octet rule. It's a boron. So you get something like this. Well, there just aren't enough electrons here. And then we could potentially form a double bond here to make it obey the octet rule. But it turns out that this isn't so stable. This isn't so stable because essentially oxygen would be losing an electron to boron. Normally we do, you have to know, because that's not a hard rule here. If it's carbon, then it's enough to do something like this. So for example, in carbon monoxide, this would be a big exception here. We want to obey the octet rule here, and so the formal charges get all screwed up. So oxygen becomes positive and carbon becomes a negative formal charge. But in this case, boron doesn't quite have the electronegativity to do something like that. And so here, it would work. Getting the octet here, it's not going to work. So you just have to know that boron isn't enough. So it's not going to obey. Whoop. What were the other ones?
SiF6 2 minus.
SiF6 2 minus. What did they say about that? Did they say it's going to obey the octet rule or not obey the octet rule?
I think this might be a typo because they don't have the minus on the solution panel,
Okay.
but they said it doesn't.
Yeah. There are two ways of doing this, something like this. One is we just maintain an octet. If we just maintain an octet, then that means just 4 of the fluorines will be bonded. And then the 2 extra fluorines will be ionically bonded. Okay, the formal charge is going to be 0. Or no, it's not 0. What is the formal charge on sulfur?
Oh, it's supposed to be silicon.
Oh, silicon, sorry. What's the formal charge on silicon would be? 0. So this is kind of weird for the bonding. And so in this case, even though the formal charge is 0, the oxidation state is what? +4 would be the oxidation. If winner takes all, then silicon's left with no valence electrons. The actual charge is somewhere in between the two limits. Formal charge, we have the limit of 100% covalent bonds. And oxidation state, we have the limit of 100% ionic bond. And so typically a bond like this, silicon and fluorine, is not going to be 100% covalent, and it's not going to be 100% ionic. It's a very polar bond. And so the actual charge lies somewhere in between these two extremes. We do the extremes so that we can make an apples-to-apples comparison, but the true charge should be between 0 and +4. And so that could be what's holding these fluorides on. Otherwise, we don't see any kind of, charge, ionic attraction. there. So the bonding is weird on this. This is while maintaining an octet, or we could just expand the octet. The situation with the expanded octet is that we need to hybridize this, sp3b2. And so this is one of the things that they leave off of chapter 11. We need additional work to nail down the bonding in this, hopefully. Theoretical work. Because this is the way it's always been. But it may not be correct. Well, did that answer that question?
Yeah. There's a lot of them that they asked, so we don't have to like go through all of them.
All right, just give me the ones that you're not certain about.
Okay.
Here, let me see if we can.
There's just one more.
I'll bring those up. All right. Okay, so I forgot to record. Yeah. All right, so we're going to jump to 1610, which is molecular structure and acid-base behavior. We're jumping into that. We have like a ranking, the acid strength chart, and so let's take a look at some of those acids there.
Professor, didn't you use to work with bases
Yeah,
like amide?
amide, right? Amide, I used to do that. Amide is an interesting one.
Did you ever work with an acid or a base that just didn't have the property? Something that didn't really qualify as an acid or a base, but was still quantified as.
Well, bases and acids could have other properties as well, because acid-base properties are just one. We have redox properties and metathesis properties too. And so the answer would be yes, because some bases will act in different reactions differently. You'd expect.
Did you ever get to create a new acid or base?
No. But the most powerful base that I've worked with is this one.
sodium in liquid ammonia.
Yeah. It makes this solution here. This is sodium and liquefied ammonia. Starts out looking like this, but it is a brilliant blue color. Did you see the blue?
I see.
The blue color?
Yes.
Yeah, it comes out a very deep blue. You can't even see the video. It's so great quality. This is extremely powerful base. It's sodium metal dissolved in liquid ammonia. Essentially has like free electrons. But it's very reactive. Lots of different things. There's a guy at USC. He's passed away though, but he won the Nobel Prize in chemistry, and he specialized in these powerful acids and bases. Is this hydrogen very acidic? Why or why not?
Carbon's not electronegative enough to the electrons to expose the hydrogen.
Yeah. Carbon's electronegativity is 3.5, something like that. Hydrogen's electronegativity is like a 3. Well, no, 3. I'm sorry, not 3.5. 2. Yeah, 2.1, 2.5. And the difference is very small. So we generate a very small delta plus and a very small delta minus. In fact, this is essentially falls into the non-polar range. That is the charge. But there is a tiny charge here. That's one thing. The other thing is this carbon-hydrogen bond is fairly strong, and it's hard to break. It's an sp3s. It's got good overlap here. It's hard to break. That's number 2. Number 3, what would the products be if you deprotonate? If you pluck off the hydrogen, we call it deprotonation. What would the products be? Product would be kind of unstable. It would be a methide anion. You know what a methide anion looks like? Well, let's say, okay, if you had a base powerful enough to pluck off, so you'd need a powerful base. And this is why, he was looking, this Professor Ola at the USC, he was looking at this because he wanted to get things like methane to react. If you have methane, there's a lot of methane. A lot of the methane, they just, what do? They just let it go into the air. Although it's a bad greenhouse gas, they let it go into the air because it's not worth capturing. So in Santa Barbara, there's always a bunch of methane leaking out into the air. And it'd be great to capture, but it's just not economical. But now they're talking about capturing it because of greenhouse gases. And then there's other places where they just let it burn. If you drive up the 101 by Rincon, there's the eternal flame. That thing's been burning ever since I've been alive. It's burning it off. It's kind of a waste. But anyway, it's better to burn it in the CO2 than leave it as a flammable gas. But anyway, we would need an exceptionally powerful base to pluck that proton off. Exceptionally powerful, because what we would form is we'd form this. What's the charge on carbon here? Not -2. Again, formal charge. Minus. And so we plucked off the proton, which is the hydrogen ion here, and we deprotonated it. So number one, a lot of bases aren't going to be attracted to this hydrogen. It just doesn't have enough positive charge on it. And so acid strength is going to depend on a number of things. Surprisingly, it's not that. You'll find, even if there's a small positive charge there, you'll find that bases will be attracted to it. Because what are bases? Bases are negative. And so the base is going to be attracted to this, but it's going to have a hard time because it needs to latch onto that proton and then pluck it off. It can if this bond is exceptionally weak, but this bond is strong. And so when we look at acid strength, the first thing we consider is the bond strength. How strong is that bond? This one is like in the mid 300 kilojoules per mole. So it's fairly strong. What do bond strengths range for covalent bonds? Covalent bonds, yeah. 100 to 1,000 kilojoules per mole. Do you guys have that down? Well, you don't necessarily have to have it, but one of the things I do, I did as a student was, if we had covered this last week, I would have already reviewed that like every day from last week, so I would have had it memorized, 100 to 1,000. The strongest bond was what? Well, was it this is a covalent bond. Was it a single, double, or triple? Do you recall what element it was?
Nitrogen.
It was the nitrogen-nitrogen bond. And this is what makes nitrogen in air fairly inert. So we can breathe this off. It doesn't do anything, right? That kind of thing. So, this is what I recommend is, it's not that you have to know all this always, but if it pops up on a test, it's nice to have had it at least. All right, so this is in the 300, in mid 300s. That's that's kind of like a medium strength single bond. Single bonds around 400, stronger end. So bond strength. This bond's hard to break. 2, polarity. The more positive charge, the more the base can latch onto that proton, And so the bigger the delta plus, the better. The best acid is going to be just H plus. It's free. And so the base has no tug of war. Here the base is going to get in tug of war with carbon. Here the base just plucks off the proton easily. This is the best acid, H plus. Well, it's not really H plus. Water is going to come along and take that. So H3O plus. But H3O plus, no problem. You can pluck the proton off that easily. And so bond polarity, the greater the polarity, the stronger the acid. 3 is the stability of the products. The more stable the product, the better. Is methide a common ion that we should memorize? Methide. Methide's not very common. In fact, methide's very unstable. It's going to be very reactive. And so methane's not a good acid. 1, its bond is too strong. 2, it's not very polar. 3, its product is going to be terribly unstable. It's not a good acid. Although, people like George Olah will try to make it an acid. They want to make it an acid because once they get methide, then they can make other things. A lot of the methane, they just let bleed into the air. But, how can you make that economically feasible? You might use that as what we call a feedstock. You use the methane to make new chemicals. And new chemicals would be longer branch chain things. And so one of the things he's working on is like synthetic gasoline. How can you make synthetic gasoline from things like methane rather than wasting the methane? So people are thinking about those types of things. And so these are the issues we're looking at. And so the weaker the bond, the stronger the acid. The bigger the charge, the stronger the acid. The more stable the product, the stronger the acid. So we end up with this. When we look at the stability of the product, this is localized. That is stuck in an sp3 orbital. We can't delocalize it. You know, delocalizing would be like, can we draw resonance forms for this? And then delocalize, that's localized, it's concentrated. The more concentrated the negative charge. So bond energies is the first one we look at. So this is how do you break the bond? There are two ways of breaking bonds. We can break bonds heterolytically, or we can break bonds homolytically. And they require different energies. We're not going to get into it too heavily. The bond energies that we see compiled in chapter 9 or chapter 10, whichever chapter that was, I think 10, are homolytic bond cleavages. And so we're looking at HX. The two ways we can break it, heterolytic or homolytic. And they give different energies. What we need to do is, well, what we're doing here is when we look at the bond enthalpies, the bond enthalpies are for homolytic. This is for bond dissociation energies. And so if we want the heterolytic energy, what we have to do is we have to do a little bit of Hess's law. Not only that, these are for gas phase, so it complicates things a bit too. And so this is what they're showing here. This is heterolytic bond cleavage here. The bond dissociation energy, which they're calling D-dissociation energy for the HX bond, is homolytic. And so if we want the heterolytic, we can either measure the heterolytic directly, which might be difficult, or we can use Hess's law. Hess's law is we need to remove an electron from H. That's the ionization energy 1, EI for hydrogen. That's minus. So if we take the homolytic and then add the ionization energy, and then we need to add an electron to X. That's electron affinity. And so what we do is we can do it in 3 steps. This plus this plus this gives us this overall. Okay? This is Hess's law. So if we don't have this, the heterolytic bond energy, then we can figure it out from these. So what we're after is the heterolytic bond dissociation energy here. And that's what we're interested in. So let's take a look here. Oh, sorry, I was off. The HC is 414. So that's pretty strong. That's stronger than I was thinking. Well, I just know the range. If you know the range, then you can ballpark it. And ballpark, I don't have the individual ones memorized. Memorize the range. And so this is 414. The heterolytic is 1717 kilojoules per mole. And so that's the one. This is the one in bold, though. But even if we don't use the one in bold, we just go off the homolytic, then we can see. And so what we're going to do is we're not even going to bother doing the Hess's law. We're just going to look at the homolytic bond energy and get an idea from that. And so getting an idea from that, we look at this and we say that which one has the strongest bond. Strongest bond looks like HF. So based on bond energies, which one should be the weakest acid? Just based on bond energy. Which one should be the strongest? The strongest should be the weakest bond.
Strongest would be H and H2, lowest number.
Yeah. This one looks like the weakest bond here. The strongest bond looks like HF. So this should be the strongest acid, the weakest bond, and that should be the weakest acid, HF. Is that the case?
No.
No, that's not the case because we don't look at just one thing. We look at bond energy plus, well, the bond energy and bond strength I use interchangeably.
The polarity and the stability.
The polarity and the stability. So when we look at the stability here, it's not just the homolytic. Here, the stability is going to be we're forming fluoride versus amide. Which one's more stable, fluoride or amide?
Fluoride.
Fluoride's much more stable, right? And so in that case, we could look at the heterolytic numbers, but when we factor in stability, this is forming fluoride, this is forming amide, and then we see that one's much better to form. And so that's going to impact the bond dissociation energy. And so when we factor in the products, then we're looking at this here. And so it turns out that the weakest bond is going to be HF. I mean, the strongest acid right now is going to be HF. And the final thing we look at is
Polarity.
Polarity. Which of these is most polar?
HF.
HF. And so HF is going to be the strongest acid out of this sequence when we consider the three factors. All right, the other way of looking at this is just strictly based on polarity. Based on polarity, out of these, which one should be the strongest acid? HF. But we should consider all three factors. Okay, based on polarity, which one should be stronger? HF or HCl?
HCl.
Based on polarity.
Oh, based on polarity, HF.
HF should be stronger. Based on bond strength, which should be stronger?
HCl.
HCl, we got a conflict. We have a conflict because polarity tells us HF should be the most polar, and so it should be the strongest. But bond strength says HCl's got a weaker bond. Which one wins? So here's where we need some two-pronged approach. Because now that we have a conflict here, we don't know which one wins. And so we just base it on which one's stronger acid based on experimental data. Which one's stronger? HCl's stronger. HCl's much, much stronger. It turns out that these numbers here are Ka. Ka gives us the kind of magnitude of the acid strength. If we look at this Ka, it's 10 to the minus 4. When we look at this Ka, it's 10 to the 6. Well, 10 to the minus 4 to 10 to the 6 is a huge difference. When we look at that, that's 6 plus 4 is 10 orders of magnitude. So HCl is about 10 to the 10th times stronger. 10 to the 10th is like 10 to the 10th would be close. 10, not 10 million, 10 billion. So HCl is 10 billion times stronger. Does that mean HF has 10 billion times weaker bond? No, it doesn't. I mean, the bond is not 10 billion times. It's not even 10 times weaker. And so why is there a huge discrepancy? And so HCl is a weird one because there's one additional factor we have to look at beyond what I talked about here, but it's only for HF. For HF, we have to do a special exception. So let's take a look at HCl, HBr, HI. When we look at this sequence, which one has the weakest bond? We could either go by the homolytic, which is found here, 431, 364, 297, or the heterolytic. It doesn't really matter. We don't have to do the heterolytic here. Homolytic should work. We do these three, and then which is the weakest? HI. Why is it weak compared to HCl? Why is HCl a much stronger bond?
Oh, because it's because it's further away.
Chlorine is going to have what? 3s, 3p, and that's going to hybridize to what? 3,
Sorry, SP3.
sp3. What's the difference between chlorine and bromine? Yeah, it's going to be the 4, so the next shell, which means the orbitals are going to be a lot bigger. When the orbitals are a lot bigger, we don't concentrate the electron cloud quite as much. The electron cloud is going to be more dilute. Therefore, the bond is going to be weaker. The electron cloud's much more concentrated here. The electron cloud is not. And so we expect better bond here. And then for iodine, we're hybridizing which orbitals? Yeah. Did I miss one? No. So the HI bond is going to be the longest and the weakest. The HCl bond will be the shortest. However, we also have to look at polarity. Looking at polarity, which one's going to be the most polar out of these three? HCl is going to be the most polar. Chlorine's much more electronegative than bromine and iodine. And so based on bond polarity, which one's the strongest of these three? HCl. Based on bond strength, which one's the strongest out of these three? HI. Okay, now our two-pronged approach, which one's the strongest out of these three based on experiment? Yeah, HI. HI is the strongest. So, we look at one final thing. What's the final thing we look at? Number 3, stability of the products. The stability of the products are, well, H plus is one of the products, so we're just going to look at the anion. When we look at the anion of chloride like this, what stabilizes the chloride? What stabilizes the chloride is having water molecules around the chloride, like this. We want to point the positive end of the water molecules and then we're going to surround it by water molecules. This is called a hydration or solvation sphere. And it just helps stabilize a charge. And so the water molecules are polar. Actually, I forgot to talk about polarity in much detail. So we're going to have delta plus and delta minuses on the water molecules. And so we're going to point the delta plus ends, towards the chloride here. And so chloride versus iodide, what's one main difference? Iodide's a lot bigger. And iodide being a lot bigger is not going to be as concentrated in negative charge. Remember charge density? Chloride's going to have much higher charge density than iodide. But when it comes to interacting with water, which one's going to have a stronger interaction with water and which one's going to have a weaker interaction? No, it's just look at the charge. Well, when we look at the charge, we have to look at Coulomb's law. Coulomb's law, the force is proportional to the charge on A, the charge on B, and the distance between the centers of charge squared. And so which one's going to have stronger attractions will be the chloride, because the distance between the centers of charges is shorter. The charge is all the same, whereas in iodide, distances are going to be much longer. And so based on bond energy and product stability, HI should be the strongest. Based on polarity, HCl should be the strongest. Based on observation, which one's the strongest? HI. HI is the strongest. And so HI. So this is kind of our ad hoc explanation, or after the fact. After the fact, we can explain anything, right? It's the prediction. And would we have been able to predict which one's strongest? No, because we don't know the magnitude. You know, how important of a factor this is versus that. We could try to make a prediction, but it'd be difficult, right? And so HI is the strongest. HI is the strongest, so that tells us what's most important. Probably bond energy is the most important. What about HF? You know, all three of these are strong acids, but what happened to HF? HF is a weak acid, so HF is an exception. This is after the fact, too. HF is like 10 billion times weaker. Why is that? If we say bond energy, then somebody's going to hit you. You know, you say, okay, HI is the strongest because it has the weakest bond, but then they go, well, what about HF? HF is 10 billion times weaker. Does it have a 10 billion times weaker bond? Then you go, well, there are multiple factors we have to look at, probably. Or are there? Well, it turns out that HF a weak acid. There are different ways we can look at this. If we have water around, then water is going to pluck off the hydrogen, make fluoride. Hydronium and fluoride. But because of the tiny size of fluoride, what happens is it doesn't completely break off. What happens is this. You can make the hydronium, and what happens is the fluoride hangs around. And so we partially have broken the bond. And then it requires one more step to free up the fluoride. That is one more collision. This is called an ion pair. Ion pair means the hydronium can't act freely. It's stuck onto the fluoride. The other way of showing ion pairing is like this in our book. Our book would show this breaking to this, breaking to this. Whereas we don't have the same kind of ion pairing occurring because the size is much bigger and the electrical interactions are much weaker. So it's showing the ion pair here, where they're kind of stuck to each other. And so it's just starting to break off here. It hasn't completely. We'll put charges on that. And so this is why HF is an exception. It's not because of this ion pairing, we need additional collisions to break it. All right, so let's take a look at some acids and then try to understand them. HOCl versus HOBr. Okay, number one, bond strength. What bond are we trying to break? The HO bond. Here we're trying to break the HO bond. This one we're trying to break the HO bond. So, tie, let's say. So if it's not bond strength, then what do we look at next? Polarity. Which one is more polar?
Chlorine is more electronegative.
Well, it's an HO bond. What's the difference in electronegativity? Hydrogen is a 2.1, oxygen is a 3.5. Hydrogen is a 2.1, oxygen is a 3.5. So they're the same, aren't they?
Yeah.
They're the same, yes. And therefore we have to look at the next. We have to dig in a little bit deeper because these would give us the same delta En. To give us the same delta En, we have to dig a little bit deeper and look at what is O attached to. In this case, O is attached to chlorine. Over here, it's attached to bromine. What difference does that make? It makes a significant difference. And so this is why electronegativities like Pauling's aren't necessarily the most accurate, because if we just look at Pauling's electronegativity and do delta En, we're going to get the same polarity. But it's not the same polarity because of what's bonded to. And so we're looking at the next. And so in this case, chlorine. Chlorine's a bit more electronegative than bromine. And so what difference does that make? It means that chlorine has a greater pull for electrons than bromine does. And so we come up with something called the inductive effect. So what we do here is we look at the electron cloud, we look at polarization of the electron cloud. When we look at polarization of the electron cloud, oxygen versus chlorine, who's stronger? Oxygen. And so this electron cloud should be polarized. Hydrogen versus oxygen, hydrogen is weaker than this electron cloud here. But chlorine is not that different. In fact, oxygen and chlorine have the same electronegativity. Pauling, so they're both 3.5, but oxygen's stronger because it's smaller. Look at HOBr. Well, number one, bromine versus chlorine, which one's bigger? Bromine's bigger, and it's also weaker. And so this bond's going to be more polarized here. In fact, oxygen is going to take the majority of the electron density. This bond's going to be pretty much the same. Whereas over here, chlorine is going to put much more of a struggle. And so this is called the inductive effect. And the way we show it is by using little arrows like this. The arrows go to the terminal. Even though oxygen is more electronegative than chlorine, we show it going like this because chlorine has a bigger pull than bromine. And so it's a little bit weird because this arrow should be pointed towards oxygen being more electronegative, but the chlorine is going to provide an additional stress on the oxygen as far as this electron cloud versus bromine. Bromine puts a much smaller stress on that oxygen versus electron cloud. And oxygen is trying to pull both from hydrogen and from bromine and chlorine. And so the end result of this is this. We're going to get a bigger positive charge here and a smaller positive charge here. So which one's going to be more attractive for bases? HOCl. So both are weak acids. HOCl is stronger. Bond energies are about the same. And the other difference would be the base. Stability, conjugate base stability. Well, let's just look at the experimental data. What does the experimental data, which one do you predict is going to be a stronger acid? HOCl. It's about 10 times stronger. All right. Here they're just using the octet. Most Lewis structures for sulfuric acid will have two double bonds to get rid of the formal charge. And so let me talk about both. So we could have one double bond, which would require one PD pi bond, or we could have two double bonds, which would require two PD pi bonds. And so I would draw it. Octet, one double bond, two double bonds, and the Lewis resonance forms for those. Versus for sulfurous acid, a lot of people do it like this. These are the expanded octet versions. The expanded octet versions are going to be much more common than the octet versions. You've seen the octet versions here in books and papers. Here it's kind of easy to see. You know, HO bond, bond energy is the same. Then we look at the next nearest. Here we have a sulfur with a +2 formal charge. Here we have a sulfur with a +1 formal charge. Which one's going to pull the electron cloud more? The +2. So we're going to have a larger inductive effect here. Because of the larger inductive effect, this sulfur 2+ is sucking electron cloud more than it normally would from oxygen, making this hydrogen much more polar. This one's sucking the electron cloud less, making this one less polar. And so based on polarity, which one's stronger? Sulfuric acid. Sulfuric acid is 5 orders of magnitude, 100,000 times stronger than sulfuric acid. What if you're doing this? What? There's no formal charge. No formal charge here, no formal charge here. If there's no formal charge, which one's going to have a larger inductive effect? Oh, then you got electronegativity, but electronegativity sulfur versus sulfur, it's the same. So we can't go to electronegativity like we did for chlorine and bromine. And so what do we do here? We could look at stability of products. That's a good one. Or there's one other thing we do. No. The one final thing we do before we go to stability of products is we look at oxidation state. Are the oxidation states of the two sulfurs the same? No. What's the oxidation state here? The formal charge is 0. We don't usually write 0 formal charges. What's the oxidation state over here on sulfur? Plus, what's the oxidation state here on sulfur? No, not 7. +4. 1, 2, 3, 4, 5, 6. Oh, actually, that's a formal charge. For oxidation state, winner takes all. Winner takes all, that means sulfur is left with 2 electrons. It's supposed to have 6. So it's lost 4 electrons, +4. +4 plus 6, those are common oxidation states for sulfur in the positive. And so which one's going to be withdrawing more electron density? A sulfur in the +6 or a sulfur in the +4? Sulfur in the +6. So once again, we're going to have greater inductive effect, resulting in larger polarity. Here we're going to have a smaller inductive effect, resulting in lower polarity. So I thought I'd talk about this because the formal charge can't always be used like we did over here. Over here it's easy. The formal charge shows us which one. And remember the true charge is somewhere in between, usually, formal charge and oxidation state. Stability of the product. Stability of the product, we have this. Sometimes things conflict. You got to remember that. And when they conflict, then we need additional data. The product is the conjugate base, or just the base. Okay. We want the base to be more stable. Therefore, the weaker the base, the more stable. What makes a weaker base? What makes a stronger base? So, since we wanted to think in terms of acids and bases, What makes a strong acid? What makes a strong acid? Weak bond, polarity, stability of products. What makes a strong base is this. And so I'll tell you what makes a strong base, and when we try to do what's opposite to figure out what a weak base is. To make a strong base, we want high charge. Whether it's formal charge or oxidation state or whatever, high charge is good. High charge, it's got to be negative charge, right? That makes a good base. This is why sodium metal dissolved in ammonia is such a powerful base, because what happens is the sodium gets ionized and we get electrons, solvated electrons. Solvated electrons, they're essentially free electrons. So we want high charge. We want localized charge. Versus delocalized. We want localized charge. There are two ways to delocalize a charge. One is the inductive effect. The inductive effect helps delocalize a charge. And two is resonance delocalization. So if we lose a proton here, we're going to form bisulfate. We're just going to lose one proton right now. Here, we're going to have the inductive delocalization. That's going to help stabilize it. This is +6 oxidation state. And so we're going to have some inductive effect here. And that'll help delocalize the charge. But the inductive effect is minor. The major effect are the resonance forms. How many resonance forms can we draw for this? Three others? Yeah, but one of them is not so good. And so we'll ignore it. Sometimes I ask people to draw the resonance forms for this. You know how many resonance forms they draw? I've seen more than 8. How do you think they got more than 8? You know how many I get? I get 3. I get 3 because fourth one with a double bond here on the oxygen is terribly unstable. So I get 3. How do you think they got so many resonance forms? I got 3 resonance forms, but some people get a lot more. You know how they get a lot more? They start moving the hydrogen. So they get 3 here with this, and then they move the hydrogen up here and get another 3 for that. And then they move the hydrogen over here, get another 3 for that, and then they move the hydrogen down here and get another 3 for that. So that's 3 times 3 is 9. We got 9 resonance forms with it. That's a lot of resonance forms. I only gave them this much space because I was only expecting them to do 3, so they had to do it on additional paper. We never move the atoms in resonance. We just want to know, if it's fixed like this, how many different ways are there positioning the electrons? Atoms never move. If you start moving atoms in resonance, then it's all wrong. Well, anyway, if we deprotonate this, how many resonance forms can we generate? Well, the third one isn't so great. And so we end up with 2. So we average the charge. So we have -1/3. That means in the hybrid, what's the average charge on each oxygen? In the hybrid, what's the average charge? -1/3 on the oxygen. Over here, we average the negative charge over 2 oxygens. What's the average charge on each oxygen? -1/2 oxygens is -1/2. And so when we look at this, we have more resonance delocalization of the negative charge here than we have over here. And so that's going to be significant. The inductive effect isn't going to be so big here. The inductive effect is minor, as I said earlier. This is +4. But the inductive effect still helps. You know? And if sometimes it's the only thing. And so which of these two is stronger? Base. Bisulfate or bisulfite? Which one's a stronger base? We want localized charge for bases. Bisulfite's a stronger base. Bisulfate is a weaker base. We could do the same thing over here. If we look at the octet, that was the expanded octet. If we look at the octet, what's the average charge on each oxygen? -1. So they both have the negative charge localized in an sp3 orbital on the oxygen. And so in this case, there's no resonance delocalization because we don't have any resonance forms for this. And so what do we look for? If there's no resonance delocalization, we look for inductive effect. Which one's going to have a larger inductive effect? A +2 or a +1? +2. And so what that's going to mean is more of the negative charge, more of that cloud is going to be pulled towards sulfur. Over here, this is going to have a smaller inductive effect. And so this might be closer to a full negative charge. This might be a little less because of the inductive effect. And so we have to look at different things depending on the structure. So this is inductive effect here. Inductive effect says that the charge is going to be more delocalized here, meaning this is weaker. And the charge is going to be more localized here, meaning it's stronger. More delocalized, more localized. Does that make sense? And so I did it both ways because it depends, you know, if you're taking a test or something, depending on the author. Talking a lot. Well, we can take a break here and then we'll look at some organic acids and then we'll talk in the jargon, you know.
Because the distance between oxygen. Wait a minute. This is for bases, right?
Because oxygen has a stronger negative charge, so it's more likely to attract a proton in hyperbromide.
Why does it have a stronger? Aren't they both -1?
No.
Okay.
The inductive effect is stronger, thus
Thus the delocalization. It's more delocalized.
it's more delocalized. Yeah. Here it's more concentrated. Here it's less concentrated because it's not. This would be the inductive for the delocalization, and so it's charge density, and so should be the stronger base. This should be the weaker base.
Yeah, I thought delocalization was like when you can move the charge around using different resonance.
Yes.
But isn't this just like
No, there's two types of delocalization. The two types of delocalization are the inductive effect and resonance delocalization. So there's no resonance forms that we're going to draw for this. And so it's just strictly due to the electronegative. Chlorine's more electronegative, so it's going to withdraw more of the negative charge from oxygen. Bromine's less electronegative, so oxygen. You know, when it comes to oxygen versus chlorine, who wins? Oxygen. Oxygen versus bromine, who wins? Oxygen wins. Oxygen wins in both these cases, but chlorine's going to put up a bigger tug-of-war fight than bromine. And so this is the wrong direction for the dipole. It shouldn't be that way, but we're doing the inductive effect. The inductive effect is just showing the difference between chlorine and bromine. Chlorine's stronger. It's going to have a stronger inductive effect, making the charge less localized. That's what we say than bromine. But anyway, try this one, acetic acid versus ethanol. Tell me which one's a stronger acid and why. So why don't you guys work on that?